Page 294. The last topic in our study of linear regression is multiple linear regression. Up to this point, we've considered the case where we have one dependent variable, y, and one independent variable, x. But in some relationships, a dependent variable, y, is a function of more than one independent variable, x, z, w. We run out of letters, so we'll just use the terms x1, x2, x3, and so on for multiple independent variables. Now, such multiple dependencies are common in areas like business and economics and sociology, in everyday life, as well as the sciences. I won't read the examples in the bullets here, but let's look at this chemical example. In a chemical process, the yield of a reaction may be a function of several independent variables, such as temperature and concentration and pressure and pH and reaction time, and on and on. So the chart below shows a three-variable linear system in which y is a function of both x1 and x2, two independent variables. Look at the equation. Y is equal to a constant plus 10x1 plus 7x2. And here's a surface plot showing this. The vertical axis is the response variable y, and the front axis is x1 from 0 to 10, and the depth axis is from 0 to about 9 or 10, and that's x2. So we can see that if you look at the front edge of this, where x2 is 0, this is the 0 line for the depth. Just considering the relationship between y and x1, we can see that as x1 increases, y increases by 10 times. And if you consider, for example, along the side wall, where the value of x1 is 0, so that's a constant, and just consider the relationship between y and x2. As x2, the depth increases, then y increases by a sevenfold factor. So it's a flat surface. Notice that it doesn't run through the origin because we have an intercept of plus 50. Equations that describe multivariable dependence might be linear or nonlinear, and those that are linear can be fitted to the form y is equal to b plus m1x1 plus m2x2 plus m3x3, and so on. Now, sometimes the independent variables are called predictor variables. We usually call them independent variables. The dependent variables are sometimes called response variables. And both Linest and the regression tool in analysis Toolpak will perform multiple linear regression just as easily as it did two-variable linear regression. And it will find the intercept b or b sub 0 and the constants m1, m2 that best fit the data. On the next page, we'll look at an example of multiple linear regression that I borrowed from a textbook called Applications of Excel in Analytical Chemistry. It's quite a good book for you Excel enthusiasts. So in this example, the extent of a chemical reaction is monitored or measured by the absorbance of the reactant as it's being consumed in a reaction. Now, the yield, or the extent of reaction, is affected by both temperature and reaction times, and both of these were measured along with absorbance. Both Linest and Analysis Toolpak regression are used to find the equation describing the data. We'll take a look at how to do this regression in Excel in a few minutes, but first I want you to look at the results with me so I can explain what's going on. So here are the time measurements between about 16 and 22 minutes. Here are the absorbance readings, and here are the temperature readings between about 30 and 60 degrees C. So we have these two independent variables, time and temperature, and one dependent variable, absorbance. We apply Linest, and it gives us the coefficients of the variables. So this coefficient is applies to the time, m1, x1, and here this coefficient applies to the temperature, m2, x2, and here's the intercept. And then we have the standard uncertainties of the temperature coefficient and the time coefficient, and also the standard uncertainty of the intercept, along with r squared, degrees of freedom, and other information that we don't probably need here. Here is the analysis Toolpak output, which gives us basically the same information, but in this case, this is one case where I happen to appreciate Analysis Toolpak more than LINES because it labels the coefficients for me, and when I have so many here, it's helpful to see what we're looking at. So again, we have regression statistics. Now it gives us multiple r. This is simply r. And then r squared is the square of r, and that's typically what we look at for two-variable regression. But when we have multiple regression, 3 or more variables, we use the adjusted r squared value. It's usually quite similar to r squared, but 0.969 in this case. Here are the coefficients, and they're labeled for us: the intercept, and then x1, recall that's the coefficient for the time values, and x2, which is the coefficient for the temperature values. And here are the standard uncertainties of them. So taking this information, we can write the equation of the line. Here it is. The absorbance is equal to the intercept, 1.990, minus 0.0360, that's the coefficient of the time, minutes, minus 0.0195 times the temperature, and here's the coefficient of the temperature. This is the equation that best fits the multiple linear regression. Now let's jump ahead. I want to show you what it looks like. So using the equation generated by Excel, I plotted an array of absorbance values. Here are the orange values in the center for various times ranging between 15 and 20 minutes, and various temperatures ranging between 30 and 60 degrees Celsius. And then I plotted them as a surface plot so we could look at it. So here, the vertical axis are the absorbance values. The front axis is the time from 15 up to about 20 minutes. Here it is here, from 15 to 20 minutes. And then the depth axis is the temperature from 30 to 60 degrees Celsius. And what do we see? Well, notice that the absorbance on the vertical axis decreases linearly as time increases on the front axis. So here, if we fix the temperature, let's look at, for example, at 60 degrees Celsius, that would be along the back wall. We can see that as the time increases over the course of time, then the absorbance is decreasing at a constant temperature. Now let's consider the response of absorbance with respect to temperature at a fixed time. We also see the absorbance decreasing linearly as the temperature increases. Look at the side wall here. This would be a constant time of 15 minutes. And notice that as we move towards the back, as the depth axis increases, the temperature is increasing, that the absorbance is decreasing. So the absorbance of the mixture reflects the concentration of a reactant, which is seen to decrease at a constant rate as the reaction progresses. I'm going to digress a little bit here for just a minute. If we fix the temperature, let's say constant temperature, the linear decline with time moving across the front is typical of a chemical reaction with zero-order kinetics. And you'll learn about this in a later course called physical chemistry. I'll just mention it here. Another case where this would happen, zero-order kinetics, also occurs in catalyzed chemical reactions, where the surface area of the catalyst is a fixed size, the catalyst surface is saturated, and so the reaction can only proceed at a fixed rate. And we'll learn more about this later, but this is a classic case of a zero-order kinetics reaction. In any case, here's the equation of the line. Y is equal to 1.99 minus 0.0360 times the time of the reaction minus 0.0195 times the temperature of the reaction. Now what do we do with this? Well, we could calculate the absorbance at any time and temperature that we choose. Now, why would you do that? Well, here's a hypothetical example. Say your company manufactures pie filling, and pie filling has sugar in it, and you have to cook your filling. Now, sugar is a disaccharide. It's made of glucose and fructose combined together to make sucrose. When you heat the table sugar, the sucrose, in the presence of water and heat, and perhaps a little bit of acid from the apples or the cherries, whatever happens to be in the pie, then the sucrose, the disaccharide, hydrolyzes. It breaks apart and produces a little bit of fructose and a little bit of glucose. So at any given time, you have all three sugars present. Each one has its own particular flavor. So if you want to choose a particular flavor for your pie filling, you need to stop the reaction at a certain point. How are you going to do that? Well, you'd monitor the extent of reaction by something like this. Now, you may not choose absorbance. There are other ways to measure extent of a reaction. In an example I gave you, you'd use a polarimeter, but regardless, we can monitor the extent of a reaction by measuring something, and then we can choose to stop our reaction at a certain point. Now, the hydrolysis of sucrose does not actually have a zero-order reaction rate. Its reaction rate is not a constant. But I mention it because it's an experiment you'll be doing in a later course, and it still serves as an example of how this type of statistical treatment is useful in industry. So in the example here, let's say we wanted to calculate the absorbance at a given time and temperature. Let's choose 17.5 minutes, which would be somewhere around here, and let's choose 45 degrees Celsius, which would be about here, and the intersection would be about an absorbance of 0.48. Now these values were just calculated from the regression equation, and so this is a perfect fit. Our data may not be perfect, but this is what it would look like if it were perfect. So putting those values into our equation, a time of 17.5 minutes and a temperature of 45 degrees C times their coefficients plus the intercept, the value is 0.48 absorbance. Again, that's the application. It's quite useful. Now we can't forecast a value from regression without talking about uncertainty. We need to always calculate uncertainty. And let's do that for this example. We can use the propagation of uncertainties formulas, which you've studied previously, and they're in the appendix of these notes. Here we have terms that are being added or subtracted together, and so we'd use the propagation uncertainty formula for addition and subtraction. The combined uncertainty is equal to the root of the sum of the squares of the individual uncertainties. When you see within two of these terms, we have multiplication going on, and that's multiplication by a constant. Why a constant? Well, in terms of the time, we are choosing 17.5 minutes. There's no uncertainty in that. It's a constant value. Likewise, if we say 45 degrees Celsius, that is an exact time. There's no uncertainty. These values of 45 and 17 are constants. So we have the case here where you're multiplying a constant times some value. So we'd use the formula for constants. And I've combined these together down here. So the combined uncertainty of the absorbance that we forecast at 0.48 would be equal to the root of the sum of the squares of the uncertainties of these three terms. This last term here is simply the intercept. The uncertainty of the intercept was 0.110. I'll show it to you in a minute. And then for the other two terms, we have the constant times the uncertainty of the coefficient. Now our constant here was 17.5 minutes in this case, times the uncertainty of the coefficient of the time, which happens to be 0065. I'll show it to you in a moment, plus the other constant, which is 45 degrees Celsius. Here, that's a constant, times the uncertainty of the temperature term, 00143. And where do these uncertainties come from? They come from Excel via LINEST or the Regression Toolpak. Let's take a look at these two uncertainties, 0065, 00143. So here in LINEST, 0065 is the uncertainty of the time coefficient, and 0014 is the uncertainty of the temperature coefficient. Likewise, you see it here in Analysis Toolpak. 0065 is the uncertainty of the time coefficient, and 0014 is the uncertainty of this temperature coefficient. And here is 0.1 is the uncertainty of the intercept value. And so we combine these together and evaluates to plus or minus 0.17 absorbance. On an absorbance reading of 0.48, that is terrible. It's terrible. 17 is about 1/3 of 48, a little bit more, so this is a large variation. We would have to report something like this. The absorbance at 17.5 minutes at 45 degrees C is 0.48 plus or minus 0.17 at the 68% confidence level. Now I know, and you know, that you can only report one sig fig in a standard deviation. I just carried an extra one. I deprecated it for calculation purposes. And so we would have to report our absorbance to one sig fig as well. This would be 0.5 plus or minus 0.2. I didn't even bother calculating the 95% confidence interval here because it's going to be so bad. Take a look at now. Why is this? Why is there so much variation? Well, the CV is quite large. I already mentioned 17 out of 48 is 35%. Well, notice the R squared, or the adjusted R squared. It's not great. It's only 0.97, and the uncertainties of the coefficients are pretty big. This is the uncertainty of the time coefficient divided by the time coefficient. If we move the decimal over 3 places, this numerator is 6.5. The denominator is 36. So 6.5 and 36 multiplied by about 3. Now it's out of 100. You can see it's 6.5 times 3 is going to be an 18 or 19 or 20% variation just in this one term on time. Take a look at the temperature uncertainty compared to the temperature coefficient. So multiply numerator and denominator by 1,000. This would be 1.4 on 20. What is that on 100 as a percent? So multiply numerator and denominator by 5. This would be about 5 plus 2 is about 7 parts. So about 7% variation on the temperature coefficient. And on the intercept, if we move the decimal place over 2 places, this will be 200. This is 11. So 11 parts on 200 is about the same as 5.5 on 100. So these are pretty large variations on our coefficients. So why is that? Well, it's not to do with the regression. There's nothing wrong with the process of multiple regression. It's not that LINES is busted or the analysis Toolpak is bad. It reflects our actual data. Let's look at the data. So you have to give this author some slack. If you were trying to measure the absorbance that's changing with time, that could be difficult to do accurately. And if it's changing with temperature, that's difficult again. So I think it's the nature of the beast. It's very difficult to measure absorbance accurately if it's changing quickly with time and if the temperature is varying. Better data would give us smaller variation and a tighter standard deviation. All right, so let's go ahead and do this in Excel, and we'll talk a little bit more about it then. This Excel file is called Regression, and we're working on the worksheet called MLR1, so Multiple Linear Regression First Example. Here's the data set. So let's select for LINES 3 columns by about 4 rows deep. That should give us everything we need. And choose Insert, LINES. Okay. Just give it what it asks. It's asking for the known y's. Here they are. Now for the known x's, we have to give it both x1 and x2 values together. We set the constant to 1. It says constant is a logical value. The constant b is calculated normally if constant is true is 1, or if it's omitted. If it's set to 0, then it would force it through the origin. We would not get the intercept value. We do want the intercept value, so set it to 1. For the stats, we also want to set that to 1, and it'll return additional statistics. And simply say OK. Here are the coefficients of the time and the temperature, and the intercept. And here are the uncertainties of the coefficients of the time, the uncertainty of the coefficient of the temperature, and the uncertainty of the intercept. Let's get one more sig fig here. I'll take 2. All right, let's do it again now. This time we'll use Analysis Toolpak. On the Data tab, choose Data Analysis, Regression. So for the y values, we're going to choose all the y's and include also the label y, and it'll label it for us. For the x values, you have to choose both x1 and x2, and let's include the labels. That way Excel will print the labels beside the coefficients, much easier to follow. For the output range, I'm going to choose cell J8. I've selected residuals, standardized residuals, and residual plots, and say OK. It says it will overwrite existing data. That's fine. And there it is. Let me clean it up a bit and then we'll take a look at it. All right, so I've got rid of a few decimal places here. There's our R value, R squared, and the adjusted R, which is the appropriate value to use for multiple regression. Notice we have 12 observations. Here are the coefficients, the intercept, the coefficient of the time, and the coefficient of the temperature. Here are the standard errors. Now we've also selected residual outputs, and they're listed here: predicted y's, residuals, and standard residuals. I'd like to show you where they come from and what they might be useful for. So up here, opposite the absorbance value, I have y prime. So y prime is a calculated value of y using our regression equation. So here I've typed in this equation equals m1 d31 right here. And that's an absolute reference times x1, which here is in B11, plus m2, coefficient of temperature, absolute reference, times x2, using the first set of data, plus the intercept, absolute reference to E31. When I press equals, it's 805, which is the forecasted value for the first reading. If I drag that down, I'll get forecasted values for all. And these are y prime values. Now, the y minus y prime is called a residual, and that's simply d11y minus e11y prime. And that's the difference between the forecasted and the measured value, and I can drag that down all the way. Now, the value at the bottom here is the standard deviation of the residuals. It's simply the standard deviation of the sample of all of these values. And then if I take the individual residual and divide it by the standard deviation of the residuals, which I've done here, equals F11 is the residual divided by absolute reference to the standard deviation of the residuals, and drag it down, I get the same thing as what Excel gives us here. So what's the purpose of this? Well, it's simply to help us identify the worst points. So you can see 1.5, negative 1.4. These are the two worst points. You might decide, should I check whether those points are valid or not? But it's a common error analysis that's done in Analysis Toolpak, and it's readily available for you to look at. We also select the residual plots. Now, I'm going to change the range of this. Right-click on the x-axis and format the axis, and let's take our minimum value as about, say, 25, for example, just to spread the data out a little more. That looks a little bit better. So what's this telling us? Well, we always want to evaluate to see if our residuals are randomly scattered above and below the 0 point. This is 0 residual. Line of best fit sits here. And if they are randomly varying and close to it, well then that's good. If in fact you saw the data was trending, say the residuals were low and then they moved high, it would suggest that Perhaps x1 is affected by x2, there's some covariance, or perhaps the data is affected by concentration or something like that. But the fact that they're randomly varying suggests that these are in fact two independent variables. It's useful to look at residual plots. So yes, that's all there is to it. It takes a lot longer to explain than it does to do it. Multiple regression is a really powerful tool, and it's something the students should be familiar with. Page 297, an application for using multiple linear regression for another kinetics experiment. We discussed previously how the rate of decrease of concentration of a reactant was linear with respect to time and temperature, and we described this as being a zero-order kinetics reaction, which is really the simplest kind. There are higher orders and more complex systems. In this example, we're looking at the rate of conversion of selenous acid in acid solution with iodide ion to produce selenium and triiodide ion and water. In this example, at least the data comes from Zumdal, your intro chemistry textbook. In kinetics, we're often taking data and trying to come up with an equation that describes the rate, a rate equation, and we'll be solving for coefficients like m1, m2, and m3, but in this case, in this particular reaction, these are exponents, and k. Now, the chemistry of this example is more advanced than you're ready for. It's something you'll cover in the 4th semester in PChem. And so I'm not going to hold you responsible for this. Let me move ahead and just show you. You'll be doing this likely manually on the calculator in 4th semester. So at that time, just think back, oh yeah, there was an example in my computer notes using Excel, and you'll find that Excel can do it much more quickly and easily than you can manually. So I'll leave it at that. At a later time, you can refer back to this if you want it, so you're not responsible for an example of this kind at this time. On page 299, here's an example from Harris's book, Analytical Chemistry, Chapter 5, another application of multiple linear regression. It's really neat what he's done here. So there are 3 solutions of acid of unknown concentration, A, B, and C, and he's trying to determine the molarity in millimoles per liter of these solutions by titrating with a standard NaOH solution, and also determine a standard deviation for each of these molarities. Now, in order to do that, you'd need at least 3 titrations for each sample to determine standard deviation at a minimum. And if you have 3 titrations for each sample and 3 samples, then that means 9 titrations. In this example, Harris is able to determine these values of molarity and standard deviation using only 5 titrations. And he did this by mixing together small but very precise portions of each acid. So for example, he mixed 2 mils of solution A, 2 mils of solution B, and 2 mils of solution C in the same flask, so we'd have 6 mils in total, and titrated the whole mixture and determined the number of millimoles of sodium hydroxide added. Then he mixed up other ratios, other concoctions, 2 mils plus 3 mils plus 1 mil, and titrated that mixture to calculate the total millimoles. He did this 3 more times with different ratios. And then in Excel, using multiple linear regression, he entered the millimoles of NaOH as Y values, and then X1, X2, and X3 are these volumes, and Excel very kindly returned the molarities of the 3 acid solutions and their standard deviations, again in only 5 titrations. Could save a lot of work. Now, to be honest, one would have to be extremely careful in delivering these volumes because, as you likely know, the accuracy or the precision in delivering using small pipettes, 1 mil, 2 mil, 3 mil, doesn't rival what you would get with a 10 or 20 mil pipette. So this would have to be done really carefully, but it's still a pretty cool example. Now, To your relief, I'm going to say you are not responsible for this type of example at this time. I will leave it with you. If you are at work sometime, you can come back and look at this and say, oh yeah, I remember this can be done, and you can follow the calculations through. There are some stipulations about number of samples to get a certain number of degrees of freedom to get all the stats you need, but it's pretty straightforward. Again, you're not responsible for this application. I want to show you some more applications, what can be done with MLR. So here on page 301, models including interaction effects can be analyzed by MLR. So what's an interaction effect? Well, look at this equation. Y is equal to B plus M1x1 plus M2x2 plus M12 x1 times x2. There's an interaction here between x1 and x2. We actually only have two independent variables, but this one's creating it as if it was a third variable. If we let x1 times x2 equal x3, a linear variable, and we'll let M12 be M3, then this equation becomes more like a multiple linear equation, B plus M1x1 plus M2x2 plus M3x3. Now, I plotted this as a surface plot in Excel because there are in fact just two independent variables, x1 and x2. So here is the value of y in response to increase in x1 and increase in response to an increase in the variable x2. So that shows it very clearly. It shows us that it is linear in both directions, and hence it is quite suitable for multiple linear regression. Now, to handle the regression in Excel, as I mentioned, we treat x1 times x2 as a third independent variable. What does that mean? Here are some x1 values that I just invented, and here are some x2 values again that I just invented, and here is the product of x1 and x2, and I treat this as if it was a third variable. So in Excel, in the y input range, I entered the y values D4 through D18. In the x input cell, I entered A4 all the way down to C18. So I entered all these values, x1, x2, and x3, as if there were three different variables. And Excel very kindly, correctly returned the proper intercept and the coefficients of the various terms, 10, 7, and 5. That is really powerful. Now in this case, I just obtained the data by plugging values of x1 and x2 into this equation, but in reality, if you had a system in which y responded to two independent variables, x1 and x2 would simply be the measurements you take along with y, the response. And then you'd get a third column by multiplying your two measurements for x1 and x2 times each other and enter it into Excel. Of course, you probably wouldn't get this type of an R squared of 1, but nonetheless, if your data is good, it should give a good return of your coefficients as required. Take a look at page 302. Multiple linear regression can be applied to polynomials, such as y is equal to b plus m1x1 plus m2x1 squared plus m3x1 cubed, and so on, m4 times x1 to the fourth power, and so on. So I'm emphasizing the 1. You can see that there's only one independent variable in this polynomial equation. Now we can do this if we substitute first order variables for these polynomial variables. For example, let's say x2 is equal to x1 squared. Let's say x3 is equal to x1 cubed. Let's say x4 is equal to x1 to the fourth power, and so on. So to generate this data set, I simply substitute random values of x into this equation and calculated values of y. But for the purpose of regression, I also wanted this x1 squared term. So simply square all the x1 values and treat it as if it was an independent variable. So in the regression toolbox, for the y input range, enter the y values, which is z4 to z15. And in the x input range, include both the x1 and the x1 squared term. That's from x4 all the way down to y15. And again, Excel correctly returned the intercept and the coefficient of the x1 term and the coefficient of the x1 squared term. I plotted this two-variable quadratic equation on a 2D plot rather than a 3D surface plot because it only has two variables. It has one independent variable x and one dependent variable y. And it certainly displays the curvature that's characteristic of a quadratic equation. On page 303 is a legitimate three-variable polynomial equation. So here we have y is equal to 400 plus 10x1 plus 7x2 minus 5x1 squared. But there are only two independent variables here and one dependent variable, hence it's a three-variable equation. And we can treat it as if it was a linear equation if we treat this term as if it was a linear term. So what I've done here is randomly generated some x1 values and some x2 values and substituted them into this equation and calculated y values. But in terms of regression, I created this artificial third variable, which is x1 squared. And then in Regression Toolpak, I entered the y values, BC5 all the way down to BC70. There's more data than you're presented with here. And for the x values, we go from AZ5 or AZ4 to include the labels all the way down to BB70. And once again, Excel correctly returned the coefficients and intercept as shown. Again, if this were real data that we were measuring, you'd be measuring x1 values and x2 values and measuring y values. But to perform regression on it, you would create this third column, which are the x1 values squared, and enter them that way in Excel. So this is what the 3D surface plot would look like for this three-variable equation with two independent variables, x1 and x2. So it's curved, right? It's not flat. Please note that in mathematics, the term linear does not mean a straight line. A linear function can be curved, and it can contain many additive terms, but each term can only have one adjustable parameter. So this quadratic function is actually linear. That is because this term x only has one adjustable parameter, b. Likewise, this term x squared only has one adjustable parameter. Therefore, it's defined as being linear. But look at the power function, y is equal to a times x to the b. This is not linear because the term x has two adjustable parameters, the a and the index b. And so, because a quadratic is actually linear, well, that's the reason we can use linear regression to find the polynomial equation that fits the data. Now, it's often possible to transform a nonlinear function like this power function to something that's linear. For example, if we took the log of both sides of this equation, what would we get? Well, we get the log of x is equal to the log of a times x to the b. And you recall that the log of a product is the sum of the logs. So that would be log of a plus the log of x to the b, which is b log x. So now it's in a linear form. We could plot this logarithmic data, this transform data, into linear regression, get the regression coefficients, use them to forecast an unknown x value, and we can also determine the uncertainty of that value from our linear regression plot. It's a very powerful tool, very useful to you in your career, as you will probably see. There's one final example here that I would like to take you through because it's a really neat example that shows you the power and application of MLR. So, glitter bottles. A clear plastic bottle containing a solution of water and Elmer's glue and glitter. You swirl them and watch the glitter settle. It takes a period of time and sparkles, and it's quite mesmerizing. So glitter bottles are used to calm special education and early childhood education students. Somebody's having a timeout, Here, watch the glitter settle and compose yourself. Seems to work, apparently. So for her technical project, a student chose to derive an empirical equation describing the glue and glitter concentrations that could be combined to achieve a prescribed glitter settling time. The more glitter you add, the longer it takes to settle. The more glue you add, the more viscous or thicker it becomes, the longer it takes to settle. Wouldn't it be nice to have an equation that describes it so we could make a recipe for amount of glitter, amount of glue, and amount of water that settles at a certain time? That's exactly what was accomplished here. So settling time is the dependent variable. It was measured as a function of glitter concentration, and then it was measured again as a function of glue concentration. And she came up with what she called a unified glitter equation, having the form time is equal to m1 times x1, the glitter concentration, plus m2 times x2, the glue concentration, plus a constant. Now, just to help us remember as we review this, GLI, glitter, comes before GLU, glue. So this is a first degree 3-variable linear equation which can be plotted as a 3D surface plot. And here is some of the data she's collected. So we have in tests 1 through 11 and 12 through 19, the glitter concentration was held constant. Here it's roughly 12 grams per liter, and here it's about 20 grams per liter. And then the glue concentration was varied from 0 to 300 in this case, and from 40 to 300 grams per liter, and the fall time was measured. And then in samples 20 through 29, notice that the glue concentration was held at 60 grams per liter, and the glitter concentration was varied from 12 to 121 grams per liter, and again the fall time was measured. And there was more data than this, I just chose this. Now, just to show you that how we check if this is suitable for multiple linear regression, we can plot these individual variables. So in this case, with the constant glue concentration of 60 grams per liter, this is the data here, she plotted, or I plotted, glitter concentration, and we saw that fall time is linearly related to glitter concentration at a constant glue concentration. That's a direct linear relationship. And then you can do the same by holding the glitter concentration constant here at 22 grams per liter, and then measuring the fall time as a function of glue concentration. And again, it's quite linear. Pretty good here, 996 in fact is the r-squared. So this alone gives us a pretty good idea that multiple linear regression will work. What's more, you can even just add these two equations together and you get a pretty close approximation to what Excel derived by regression analysis. If you check later, you'll see this simply is the addition of these two equations. It's quite close to what Excel derives. I want to jump ahead and take a look at the results to show you what's going on. So when this data was entered into Excel, using Analysis Toolpak and LINEST, these coefficients were given. 0.211 times x1, which is glitter concentration, plus 0.173 times x2, which is glue concentration, minus our intercept of negative 4.311. So taking this equation, I then calculated the fall time at various glitter concentrations and glue concentrations and put it up in a table here and then plotted it as a surface plot. So we can see the vertical axis is the fall time, the front axis is the glitter concentration, the depth axis is the glue concentration. So let's consider moving along the back wall where the glue concentration is constant at 250 grams per liter. We can see that as we increase the glitter concentration from 10 to 120 grams per liter, the fall time increases. Seems reasonable. Likewise, if you consider the side wall where the glitter concentration is constant at 10 grams per liter, you can see that as the glue concentration increases on the depth axis, then the solution becomes thicker and the fall time increases as well. Notice it's a flat surface, and that's a good representation of a multiple linear regression application. So let's use our glitter equation here to calculate the fall time for a selected glitter and glue concentration. So here I'm choosing 100 grams per liter of glitter and 200 grams per liter of glue. Intersection is 51. If you actually put these values of glitter concentration and glue concentration, it calculates to be 51.4 seconds per centimeter. Now, once again, we can't talk about a forecast without talking about uncertainties. And again, it's the same as we saw before. We have three terms that are combined by addition and subtraction. So we use the combined uncertainty as the root of the sum of the squares of the individual uncertainties. And we have two terms where we're multiplying a constant times a value. So we combine these two propagation of uncertainty formulas, and it looks like this. The uncertainty of the time we forecast will be equal to the root of the sum of the squares of the individual uncertainties. This is the individual uncertainty of the intercept. And here we have the constant for glitter concentration, which will be, in our case, 100 grams per liter, times the uncertainty of the glitter concentration, which we'll look at in just a moment. It's 0097, plus the constant for the glue concentration, which is 200 grams per liter, times the uncertainty of the glue concentration coefficient, which in this case is 0038, and we'll look at it in a minute. We combine these together, and we get 1.4 seconds per centimeter. Let's take a look at these coefficients and uncertainties so you know where these are coming from. This is Analysis Toolpak. Here are the intercept and its standard uncertainty. Here's the glitter concentration and its standard uncertainty, and here's the glue concentration, its standard uncertainty, 0038, 0097, 0.719. So we'll go back and look at that again. So just so it's clear, when you want to calculate fall time, when you want to calculate y, you multiply the glitter concentration and the glue concentration, these constants, times the coefficients. But when you want to calculate the uncertainty associated with it, you multiply, again, the constant, but this time multiply by the uncertainty of the glitter concentration coefficient and the uncertainty of the glue concentration coefficient. These are the uncertainties of glitter and glue. And when you do that, 1.4 seconds per centimeter is the fall time. Now this CV turns out to be pretty good, because 1.4 relative to 51.4 is the actual value, is about 2.7%, so it's just under 3% CV, and that's pretty good. Now recall, if you will, the adjusted R squared was 0.987. Let's take a look at that. So up here the adjusted R is 987, which was better than the previous example where it was 0.97. Also, the relative uncertainties are better in this case. So I don't mind expanding this one up to a 95% uncertainty. Recall the formula is the population mean is x bar plus or minus t times s over root of n. N is the number of samples. T is the t-value, which we get from a t-table or use an Excel function, equals t.inv.2t. It's a two-tailed test. So for that, you'd specify n minus 3 is the number of degrees of freedom. That's 27 is the degrees of freedom. And if you check that, the t-value is 2.052 times the standard deviation of 1.4 up here, divided by the root of the number of samples, gives us 51.4 plus or minus 0.5 seconds. And that's pretty good. A very narrow forecast. Now I know this application may not seem much like chemistry, but I think it really shows how multiple linear regression can be applied to many applications and technologies, and even in what you might call the soft sciences. Let's take a look at this in Excel. This Excel worksheet is called MLR Glitter. So let's get LINEST first. We'll select 3 columns, 4 rows deep. Insert a function. LINEST is good. The known y's, these are the fall times. We'll choose all of them. The known x's will be all of the x1 and x2 values, the glitter and glue concentrations, take them all. Our constant is 1. Our stats value is 1, and OK. So here are the coefficients for x1 glitter and for x2 glue and for the intercept. Let's do it again now with Analysis Toolpak. I'll choose Data, Data Analysis, Regression, input the Y range. I'm going to include the labels this time, fall time. Input the X values. Again, I'm going to include the labels. And check off labels are included. 95% confidence level. The output, I'm choosing G14, residuals, standardized residuals, and residual plots. And overwrite, that's fine. Let me tidy this up and we'll take a look at it. All right, so here are the results of the Analysis Toolpak regression tool. They're essentially the same as we saw with LINEST. I want to point out one thing to you, is that in Analysis Toolpak, the coefficients are given intercept, glitter, and glue concentration. And in LINEST, they present in reverse order, glue, glitter, and intercept. So be careful here. LINEST does not label these labels I've put in. And so it can be difficult in multiple regression, since we're not really plotting and getting the equation of a line on a plot. And for this reason, I kind of like Analysis Toolpak as it labels it for me, so it's very clear as to what coefficient belongs to what variable. Analysis Toolpak also prints out predicted Y values, then the residuals, and then standardized residuals, and then gives us plots for each. And what do we do with these? Well, we look at them and notice that the deviations are random above and below the line of best fit, and that's good. Also, they're pretty tight, as we saw. R squared is decent, it's pretty good. And really, that's all there is to it. So multiple linear regression is very easy to do in Excel. It's a very powerful tool that you may find some application for in your place of work. Hope that's been helpful. Thanks for watching.